So we will continue our discussion about dimensional analysis. The next application of dimensional analysis is to derive the formula between different variables. There are various steps which we must remember to derive formula using dimensional analysis. So the first step is, suppose one variable q is given to be depending upon three variables x, y and z. In the second step, we will suppose that the given variable is proportional to x power a, y power b and z power c. In the step number 3, we will combine these into a single relation. Now we will convert this relation into an equation, and we know that whenever relation is converted into an equation, then a constant of proportionality will come. After converting proportionality into equality, we will convert dimensions of all quantities, that will be q, x, y, z and constant of proportionality k. So here it should be remembered that if the dimensions of the constant k are given in the statement, then we will use these dimensions while deriving the relation. Otherwise, we will take the dimensions of k to be m0, L0, T0. That is, if nothing is said about the constant of proportionality, we will take it to be dimensionless. After putting the dimensions of all quantities in the equation, we will simplify, and by using mathematical relations, we will find the values of a, b, c. Once the values of a, b, c are found, then we can write the formula between q, x, y, z like this. So this is the last step which is written here. After finding the values of a, b, c, we can put these values back in the equation number 1 and then the formula will be derived. Let us now take an example. Suppose it is given to us that the kinetic energy K depends upon mass of object and velocity of object. So we have to find the expression for kinetic energy using dimensional analysis. Let us now derive this formula using the steps described earlier. So it is given to us that kinetic energy K depends upon two variables. So we will assume that K is proportional to m raised to power a and velocity raised to power v. Now we will convert this proportionality into equality, and C will be a constant of proportionality. So this is the C is the constant of proportionality. So in the next step, we will put the dimensions of all these three variables. So nothing is said about the constant of proportionality C in the statement. So we will take it to be dimensionless. So let us put dimensions on both sides of this equation. So the dimensions of K are ml2 t minus 2 because it is energy. So dimensions of C are m0 L0 T0. M being mass, so its dimension will be capital M. V is velocity, so its dimension will be Lt minus 1. And the powers of mass will be A and that of velocity will be B. If we open these brackets and simplify it, we will get ml2 t minus 2 equals to m raised to power a, l raised to power b and t raised to power minus b. Let us now equate the powers of different dimensions on both sides of the equation. So if we compare powers of m on both sides, then we can see that the power of m is a on the right side and the power of m is actually 1 on the left hand side. So we will get a is equal to 1. If we compare the powers of L on both sides, you can see the power of L on the right side is B and the power of L on the left side is 2. So we will get B is equal to 2. So we have found the values of A and B. Now we can put these values of A and B in the equation number 1. Let us see what will be the formula. So the obtained values of A and B are now put in the equation number 1. And hence the formula of kinetic energy becomes cmv square. Please remember that the value of constant of proportionality is not given to us, so we have written it to be as C. But in actual practice, the formula for kinetic energy is half mv square. Actually, this half is nothing but this constant of proportionality C. Thank you.